Welcome to the third and final lesson on waveforms and signals. This lesson focuses on SignalMetrics. There is a large amount of analysis that can be performed looking at the signals coming off of a sensor or the signals being processed by your microcontroller. But let's start with the basics. Signals most often have some static content, so some content with zero frequency, and that's typically referred to as a DC offset. So if we were to take the average of all the points in our signal here and compare that to the zero voltage line, this would be the DC offset of my signal. And the way to write this mathematically will be y bar, the average, is equal to the integral from t1 to t2 of y of t, that'll be my signal, and we'll divide that by the time period, t2 minus t1. So if we were looking at a periodic signal, I'd really be integrating not from t1 to t2, but more likely from 0 to capital T. So I'd integrate across one period. But ultimately, we can apply this generic concept of a DC offset to any signal that we're working with. And the DC offset is important because often I actually want to remove the DC offset. This could be something as simple as wanting to center your signal on your oscilloscope display, or just removing a DC bias in a signal such that I can compare, let's say, two different signals with the same DC offset, in this case, bringing them both to a DC offset of 0 for analysis. And that's really effectively what we're doing here. We have our original signal in black with a DC offset, and if I want to center that, I'll bring that down and remove that DC offset so that the average of my blue signal here is at 0 volts. Now, if we look at this plot, we may think it's a random assortment of dots, but in fact, this is a sampling of the original signal from last slide and the previous slide. And I calculate the DC offset for a sampled signal in a similar fashion as how we calculate for a continuous signal. Here, y bar, the average or the mean of my sampled signal, is going to be equal to quantity 1 over n, and will be the number of samples that I have taken from my signal. And we'll multiply that by the summation of all the sample values in my signal. So we'll go from I equals 0 to n minus 1, using a 0 index here, and we'll add up each value, each y value, in this case the signal amplitude of each sample, add them all up, and we'll divide them by n, the total number of samples in my signal. And so thus, here we're looking at a discrete sampled signal, but we're also able to calculate the DC offset in the same fashion that we were able to calculate the DC offset using an integral in the preceding slide for a continuous signal. So the DC offset gives me an idea of the static portion of my signal, the portion with a 0 hertz. If we want to get an idea then of the dynamic portion of my signal, we'll use the root mean square. So here I have again my signal y of t is equal to 5 times the sine of t, and my RMS value is going to be defined then as the root of the mean of the square of my signal. So I'll take the square root of the quantity 1 over t2 minus t1 times the integral from t2 to t1 of y squared of t, effectively the root of the mean of the square. And for periodic signals, we can use t1 equals to 0 and t2 equals to t, capital T, right? The period of the signal. So let's take a look at what this means graphically then. In this case, my red signal is my 5 sine of t. My blue signal will be the square of that, or 25 sine squared of t. And you'll notice, since we have the square of the signal now, 25 sine squared of t, there's no negative component to the blue signal. And I go up to an amplitude of 25. And my magenta signal here is my RMS value of my dynamic signal. And although it looks static, it's just a straight line here, my RMS value is actually giving me some information on the amplitudes of my signal here. So it's giving me some sense of the variation in my dynamic signal. We can also have a root mean square for a discrete signal. And in this case, we'll replace that integral with a summation. So for the discrete signal, I still have my root, I still have my mean, that'll be 1 over n, that's the number of samples in my discrete signal. And now I'll sum the square of each sampled value. So I'll sum each y sub I squared. And again, this is now for a discrete sampled signal. A great example of applying this concept of root mean square values is to take a look at line voltages. So a line voltage is the voltage source, say, in your wall that you're plugging your laptop power supply into. Now you might think of this as a 110 volt or 120 volt signal. However, that signal is actually something more like 170 times sine of quantity 2 pi times 60 times t, where now I'm using little f as my frequency. So I've got a 60 hertz frequency in terms of time in hertz coming through the wall, and I have a amplitude of 170 volts. But when you RMS this voltage coming off the wall, the RMS value is actually 120 volts. And that's what we tend to think of when we think of the voltage on the wall socket at our wall at home. But it's important to realize that's not the amplitude of the signal. 120 volts is actually the RMS value.